composite structures for these structures. So let's see. So first of all, we will see how a composite structure is made. So we can say that composite structure, composite, we know that it is a combination of two materials. So we can say one is the matrix and the another material is fiber or reinforcement. So matrix, we can see that these are the matrix, which is the bulk material. Matrix is the bulk material, which is in large amount, and fiber, which we can see these are fibers. These all are fibers. So these fibers are very strong or very high strength because its size is very small. Basically its size is 10 micron meter. So we know that the smaller the size of the material, higher the strength. So these fibers are very high in strength, and the bulk materials, means the matrix, are lower strength. So the overall strength of the lamina, which is made from the matrix plus fiber, this is called lamina. Lamina is a plate layer. So this structure, which is in the direction the fiber is oriented, so fiber is oriented in the direction 1, so it would have a high strength in the direction 1, and other than the direction 1, in direction 2 and 3, it will have very low strength. So we will see here. So it exhibits highest strength and modulus, means modulus of elasticity or Young's modulus of the fibers, and very low in the transverse direction. So high strength and modulus in the direction of the fiber. In this direction, we will have very high strength in the direction 1, and low strength in the direction 2 and 3. We will have very low strength. Now it is treated as an orthotropic material. So it is treated as an orthotropic material. So we will see that what is orthotropic material. We know that anisotropic material, anisotropic material. So anisotropic material, we don't have, we can say that in anisotropic materials there are a number of independencies. So it is directional dependent, directional dependence. So we can say that orthotropic is one of the subset of anisotropy. Orthotropy is the subset of anisotropy, where we are having 9 unknowns. So we are having here in this orthotropic material, we are having 9 coefficients. 9 coefficients, which is E1, E2, E3, means Young's modulus in the direction 1, direction 2, direction 3. Similarly, G1, G2, G3, that is the shear modulus in direction 1, 2, and 3. And similarly, the Poisson's ratio effect, nu1, 2, Poisson's ratio nu2, 3, and Poisson's ratio nu 3, 1 or 3, 2. So these are the unknowns which we are having, 9 unknowns in the orthotropic materials. So how we get those things? So micromechanics approach used to determine the engineering constants, and which is based on the assumptions as follows. So what are the assumptions? So for this approach, for the unidirectional lamina or fiber reinforced lamina, what we are having the assumptions? The first assumption is that there is a perfect bonding exists between fibers and the matrix. So this is the fiber. These are the fibers, and this is the matrix. So there is the perfect bonding. So these fiber and matrix have a very nice bonding here. Fibers are parallel and uniformly distributed throughout. So this is parallel to this. So it is oriented in a directional manner, not randomly. So parallel and uniformly distributed. And the matrix is free of voids. So what we assume that the matrix, there is no voids in this matrix, and there is no cracks, micro cracks, and initially there is no stress developed in it. So it is a stress-free state. Now, both fibers and matrix are isotropic. So this is also one assumption that the fibers and matrix both are isotropic and obeys Hooke's law. And the applied loads are either parallel or perpendicular to the fiber direction. So the applied load is either parallel or perpendicular to the fiber direction. So either we can apply from this side that is perpendicular, or this side. Now we see that homogenization